Hello, class. This is Mr. Hart. And in this podcast, we want to talk about the next part of the forces unit, which is on horizontal and friction forces. And especially on friction forces today, we want to look at how friction occurs, how we account for it mathematically, and how it's going to affect our force diagrams that we've been drawing. Okay. So you may recall from a while back when we just looked at forces, okay, that we kind of described friction this way. Okay. So friction is the force caused by resistance to a movement across a surface, okay, or parallel to the surface. Now, if you remember, normal force is always perpendicular. Friction is always going to be parallel to the surface, okay? So as something moves across the surface, right, it kind of bumps into the little divots and bumps in the other surface, right, because nothing's perfectly smooth. And so as they're trying to move, they're going to get some resistance across that surface, okay? And this often causes heat, okay, that's generated on both the surfaces because you're breaking some of the intermolecular forces between the different molecules in the surface, and as you do so, they release energy, which turns into heat, okay. This is why when you rub your hands together like this, right, you often can feel heat generated between them because there's a very small amount of energy that's being released by the intermolecular forces, okay. And so there's actually a small amount of molecules that are being rubbed off your skin, basically, when you do this. Okay. So if you did this long enough, for a very long time, you'd eventually get down to the bone. But I don't think anyone's ever done that long enough to actually get there. Okay. So point is, right, you're generating energy, you're bumping into molecules, they're getting knocked off, bumped into, okay, there's a force that's occurring. Okay. So on average, that overall phenomenon of trying to move across a surface that isn't perfectly smooth is what we call friction. Okay? So we got to think of a way to account for it mathematically. Now, it's not going to be something as simple as just, a number for one surface, okay? There's amount of friction for wood or something. That doesn't make a lot of sense because it's going to depend on what the other surface is, right? If I put a block of ice on wood, that's going to move more smoothly than a piece of metal on wood or another piece of wood on wood. Okay, so we need to be able to describe the interaction between pairs of surface. Okay, so there's been lots of experiments on this to try and determine about what level of friction there is between these surfaces. Okay, and the best way they found to describe this is to describe what they call a coefficient of friction. Okay, it's going to be represented by the Greek letter mu. Okay, so the spelling, just in case you're wondering, and I think we've talked about this before when we talked about the micro, right, in scientific notation and in prefixes. That's often a unit is micro, like micrometers. Okay, this is the Greek letter mu, okay, spelled mu, okay, and it represents the coefficient of friction. Okay, so mu sub k is coefficient of friction. But basically what it describes is the amount of friction between two surfaces. Okay, and it's going to be pretty consistent between any two surfaces of the same type. So basically I could say, for example, if I'm pushing ice across wood, okay, that mu sub k may be about 0.07, okay? Whereas if I'm pushing, let's say, wood across wood, that's going to be a higher coefficient, okay? And so we might say it's like 0.21 or something, okay? It's there's 3 times as much friction on wood against wood compared to wood against ice. Okay, so every single surface type compared to another surface type can be assigned a coefficient of friction on average. Again, there's smoother types of wood. Okay, there's smoother metals. There's always going to be a little bit of variation, but overall we can kind of assign an average coefficient that describes how much friction there is. Okay. So the larger the coefficient, the more friction there is. Okay, if the coefficient ever gets to 0, then that's ideally a perfect frictionless surface. Now, we don't ever see that in real life, but that's the idea. Okay, so mu sub k, it's just, you can look these up in tables or they're going to be given to you in the problem. Okay, but they just described how surfaces interact, how much friction there is. Okay, so let's look at how we mathematically account for this. Okay. So the equation we're going to need and we want to write down is this, okay? This describes the friction. So the friction force is equal to mu sub k times the normal force. Okay, so F sub k is the friction force. Mu sub k we just looked at is the coefficient of friction for the two surfaces. Coefficient, I think I spelled that right. And then F sub n is the normal force. Okay. Sorry, my handwriting is a little sloppy today. Okay, so friction force equals the coefficient of friction times the normal force. Okay, and the way I like to think about this is basically in most cases the normal force is going to be equivalent to the gravitational force for any time there's a flat surface. And so the way you can describe it is basically how much friction you have is how much friction you have between the surfaces, or how much amount of friction. It's kind of weird to think about, but how much friction you have between the two surfaces times how hard you're pushing into the surface, right? How much weight you're putting down on the surface, okay? Because a big heavy block, for example, is going to have more friction than a light block as it's going across. So the amount, how hard you're pushing into the surface, how much weight you have on the surface is going to affect the friction. Okay, so basically what intrinsic properties we have between the two surfaces, which is the coefficient, times by how hard we're pushing into the surfaces, gives us our total friction force. Okay, so we use the normal force right here because in reality this is the more important force. They're usually equivalent, but if you had an angle, for example, the normal force is going to be in this direction and the gravitational force is going to be straight down. Now it turns out the perpendicular force is more important because that actually describes how much you're pushing into the surface. Okay, so if you're at an angled surface, it may not necessarily be the gravitational force, that needs to be the normal force. But in a lot of cases, they do end up being the same. Okay? All right, let's go through a couple problems. I think this will become clear what this means and why it works this way. Okay, so let's say we have this. So an object has a weight of 46 newtons as shown. If the coefficient of friction is 0.4, what is the net force on the object? Okay, so we have this force diagram over here. Okay, and we're trying to describe how much friction we have. Okay, what's this force going back? Okay, now if this is on a flat surface, then we can assume that the weight is going to be the same as the normal force, right? So the normal force is 46 newtons. Okay. So to find how much friction force we have, we're just going to plug it into that equation. So F sub k equals mu sub k times F sub n, which in this case gives us 0.4 times 46 newtons. Okay? And when we put that in our calculator, 0.4 times 46, we get 18.4 newtons. Okay? So that's how much friction force we have right here, is 18.4 newtons. Okay, so if we want to find the net force on the object, all we have to do is take 35 minus 18.4, and that will tell us that the net force on the object is 16.6 newtons. Okay, and there we go. So that is the net force on the object. Okay, and that's the answer to the problem. So again, the key here is finding the normal force, which is usually equivalent to the gravitational force, timesing it by its coefficient of friction, and then that will give us the total friction force. Okay, how hard the object's pushed into the ground and how much friction there is between the two surfaces determines the total friction force. Okay? All right, let's look at another problem. So this time we're not given as much information. So we just have that we have a polar bear. Of course, there's always a polar bear on a sled. This is a classic physics problem because you always see polar bears sitting on sleds, of course. But anyways, he has a mass of 450 kilograms. Okay, you have a coefficient of friction between the sled and the snow of 0.7. How much force is needed to get the sled moving? So let's think about this scenario. So we know, let me do these in yellow. So we know that the force going down, okay, is the weight of the polar bear. So we're going to need to calculate that based on the mass. Now, because he's not plowing into the ground or flying to the sky, we should assume that the normal force is going to be the same as the gravitational force. And then there's going to be some friction, right, caused by the friction between the sled and the snow. And then this applied force needs to be greater than that friction force. So we're trying to find basically the friction force so we can figure out how much the applied force needs to be. Okay? So let's just start doing some calculations. So first of all, let's find the weight of the polar bear. So we're just going to take 450 times it by gravitational acceleration, which is 9.8. Okay? And that gives us that the total weight of the polar bear is 4,410 newtons. Okay, so that's this weight right here. Now, because it doesn't say otherwise, we can safely assume that the normal force is 4,410 newtons. Now that we have the normal force, we can find the friction force by timesing it by 0.7. So the friction force is 0.7 times the normal force, 4,410, okay, which gives us that it's 3,087 newtons. So this is 3,087 newtons. All right, so there we go. I'm going to erase this stuff right here really quick so we can kind of clarify what we're doing. So we use the mass to get the weight, okay, of the polar bear. We use the weight to get the normal force because they were just the same. And then we use the normal force to get the friction force by using the coefficient of friction. Okay? So now to answer our question, how much force is needed to get the sled moving? Well, it just needs to be greater than the friction force. So these two forces we want to keep balanced because obviously we don't want to plow into the ground or fly into the sky. Okay? But these two forces we don't want balanced. In fact, we need this force to be greater. Okay? So basically, our answer is it needs to be greater than 3,087 newtons. Okay? That's the only way that this object will start moving, is if this is greater than the friction force that's being applied. Okay? So there we go. So you can write your answer as greater than 3,087 newtons. Oftentimes in physics, this is kind of a weird convention, but we assume that if you put 3,087, that you mean it means greater than in this type of problem. So you can just say 3,087 newtons. It's kind of a weird convention, but that's also the correct answer. Okay, so basically once you get past 3,087 newtons, then you start moving. Okay? All right, so there we go. All right, let's do a couple more just to kind of get used to the problems like this. Okay, so let's say we have this problem. We have a car driving down the road to the right and has the following free body diagram. Okay, what is the coefficient of friction between the car and the road? Okay, so we're given all the different forces. We're trying to find the coefficient of friction this time. Okay, so let's think about our equation first. We have F sub k equals mu sub k times F sub n. So if we're trying to solve for mu sub k, we're going to basically take the ratio of F sub k over F sub n. Okay, so we're just going to divide F sub k by F sub n. Okay, so let me just rewrite this. So that's going to give us that mu sub k equals F sub k over F sub n. Okay, so we have F sub k, we have F sub n. Okay, so we can calculate this right now. Notice that the problem gave us the applied force, but we don't really need it. Okay, this is a common thing to do in physics problems, is give you extra information. Okay, so we don't really need that. All we need is the normal force and the friction force. Okay, so that's just going to be 500 newtons over 9,700 newtons. And that's going to give us that mu sub k is 0.052 about. Okay, 0.052. And there we go. Now a lot of students ask, well, Mr. Hart, what are the units for the coefficient of friction? And there actually isn't any, because you start with a force, you times it by the coefficient of friction, and you end with a force. So they should stay in newtons. So there's actually no units for mu sub k. And that's why it's called a coefficient. Coefficient actually means unitless. Okay? It's a unitless multiplier, basically. Okay? So there we go. So mu sub k is 0.052. Okay, that's the coefficient of friction. Okay? All right, let's just do one more. More practice, the better, right? And then I think we'll be good. So last problem. Okay, so we got a 12 kilogram crate. It's pulled along level ground. The force exerted to pull the sled is 10 newtons. Okay, find the acceleration of the sled if the coefficient of friction is 0.0765. Okay, so let's first of all just identify what we know. So for the sled, okay, we know that we have I guess I should say crate, huh? For the crate, we have 10 newtons of force going this way, right? 10 newtons of force being applied, okay? We know that we have a weight that we'll be able to calculate in just a second from 12 kilograms. The normal force will be the same, according to the problem. And then we have a friction force, okay, going this way. So if we want to find the weight, we'll take 12 kilograms, times it by 9.8 meters per second squared. Okay. That gives us that the weight is 12 times 9.8, 117.6. Okay, so we have 117.6 newtons, okay, going down, which means we'll have 117.6 newtons going up. Okay, so now we have the normal force. So now we can calculate the friction, okay, from the normal force just by plugging it into the equation. So F sub k equals the coefficient of friction, which is 0.0765, times the normal force, which is 11.7.6, okay, newtons, which gives us, put that in our calculator, 0.0765 times 11.7.6. And you should get that that is basically 9.0 newtons after it's rounded. Okay, so we have 9.0 newtons going this way. Okay, so now after we found that, we got all the diagram down. Now we're trying to find the acceleration. Okay, so we're going to have to plug it into F equals ma, or more specifically, F over m equals a. Okay, force over mass gives us the acceleration. Well, we know the mass is 12 kilograms. We know the net force is actually 1 newton to the right, because it's 10 newtons minus 9 newtons, which gives us 1 newton. So we can replace F with 1 newton. Okay, that's the net force. And we can replace m with 12 kilograms. And that will give us the acceleration. Okay, so we do 1 newton divided by 12 kilograms. Okay, when all is said and done, we get that the acceleration, I'm running out of space, is 0.083 meters per second squared. Okay, and there we go. So that is our acceleration, 0.083 meters per second squared. Okay, so a lot of steps. Let's review quickly a lot of the tools we can use and things we can use. Okay, we can use the mass of an object to find its weight. We've done that many times. We can use the weight of an object to find the normal force because they're equivalent. Okay, we can use the normal force to find the friction force using the F sub k equation. Okay, we can find the net force by minusing the two applied forces from each other, okay, or the two horizontal forces from each other. And then we can find the acceleration by using F equals ma, okay? And that's what we did for this problem. So a lot of steps, but if you can get this down, then there's no problem in forces that you can't solve, okay? So hopefully this all made sense. There's a lot of stuff to cover, but let me know if you have any questions, and thank you for watching.